The chi-square test for independence versus homogeneity. A test for independence is conducted when a question is asked regarding an association between variables in one population. A test for homogeneity is conducted when a question is asked regarding the distribution of one variable among two or more populations. Groups will have been sampled or assigned according to the design of the study. So let's read this problem and decide whether we should conduct a test of independence or a test for homogeneity. A large producer of over-the-counter pain management medicine has developed 3 different formulations and wishes to determine if one of them has a greater effect on pain reduction. 1,000 people were randomly selected. Each subject used one of the pain management formulations without knowing which they were using. They then reported their experiences. The table summarizes the data. So here we have formulation across the top. So we have 3 different formulations, A, B, and C. And then in the left-hand column here, indicating on these rows, we have the reported reduction. We have a mild reduction, moderate reduction, and strong reduction. So since these simple random samples come from 3 different populations with numbers of patients assigned to each formulation prior to treatment, we should conduct a hypothesis test for homogeneity. So here then would be our hypotheses. Our null hypothesis would be that the 3 formulations are homogeneous with respect to effectiveness in pain reduction. In other words, there is no difference among the 3 formulations in their effectiveness in pain reduction. The alternative hypothesis then would be that the 3 formulations are not homogeneous with respect to effectiveness in pain reduction. In other words, one or more of the formulations is more effective than the others. So we will conduct a chi-square test. And we remember that the chi-square test formula looks like this. We're going to add up a bunch of terms, and those terms are going to consist of the difference between the observed and expected values, and then squared, and then divided by the expected values. So what's going to happen then is, according to these ratios of people that were assigned to the different groups, will the expected values vary a lot from these observed values? What we will need in order to do this is a chi-square critical value and then a chi-square test value. Now, in order to find the chi-square critical value, we will need to know the number of degrees of freedom. And the degrees of freedom will be just the same as it was for the test of independence. We have the product of 1 less than the number of rows and 1 less than the number of columns. So we have a 3 by 3, so that'll be 2 times 2, or 4. So we have 4 degrees of freedom. On the AP Statistics exam, you will have some tables provided, and these tables will be distributions that you will need in order to find critical values or probabilities. And on this chi-square table, we'll find that across the top, we have the area in the tail. So if our alpha level is 0.05 and we have 4 degrees of freedom, then we would find that critical value here at 9.49. If we were to use a utility like StatCrunch, we would press Stat, Calculators, chi-square. Our degrees of freedom would be 4. And we would put the accumulated area up to that point, if we leave this at less than, at 0.95 in order to correspond with the same value. We hit compute and we find 9.488 if we round to 3 decimal places, or 9.49 if we round to 2, as in that table provided on the AP Stats exam. In order to find the chi-square test value, we can use the TI-84 calculator. We'll press second matrix, and I have already typed the values into matrix A. So we'll go over here to edit and look at them. And we can see these values are here. And then in order to get the calculator to calculate the test value and the expected values, we'll push Stat, go over to Tests, go to chi-square test, which is C, select that, tell the calculator which matrix contains the observed values, and then tell it which matrix we would like to contain the expected values. Hit Calculate, and here we have our chi-square value, 73.945. Seems like a pretty large chi-square value, and we'll look at that in a second. First, let's look at the matrix that contains the expected values. That would be matrix B, and so we'll go over to Edit and then select 2. And here we have the expected values. And recall that one of the conditions of the chi-square test is that each of the expected values is at least 5. And we can see that each of these expected values are considerably greater than 5. So our critical value was 9.488, and our chi-square test value is 73.945. So our decision should be to reject the null hypothesis. Now let's look through this table and note that the responses have a pattern. For formulation A, we can see that we start with 126 in the mild reduction response, and then that decreases as the strength of reduction increases. Formulation B has the opposite effect. We start with 85 mild reduction, and then that increases to 98 when we get to the moderate reduction, and 123 responded a strong reduction for formulation B. And then formulation C has an even more extreme variation. Note that there are 72 in the mild reduction response, 104 in the moderate reduction response, and then 216 in the strong reduction response. So while we see a pattern in the data itself, the chi-square test verifies that this is a significant pattern and we do not have homogeneity between the groups.